In this lecture, we're going to be looking at orbital mechanics. So if you want to read over this in the textbook, have a look at sections 13.6 and 13.7 in Halliday, Resnick and Walker. So first of all, a quick recap of the most important ideas from the last lecture. In the last lecture, we saw Newton's law of universal gravitation, which tells us that the gravitational force between two particles with mass m1 and m2 separated by a distance r is given by F is equal to g m1 m2 on r squared, where g is the universal gravitation constant. We saw that for an object placed on a rotating body, such as a planet, then the normal force, which is analogous to what the scales measure, is given by minus m omega squared r plus g mm on r squared, where the little m stands for the mass of the object and the capital M stands for the mass of the planet. The capital R here is the radius of the planet. We saw that gravitational potential energy is given by U is equal to minus G mm on R, and here the potential energy is taken to be zero, an infinite distance away. And we then showed that the escape speed for an object is given by V is equal to the square root of 2gm on R. So this is the speed that an object needs to leave a planet with in order to get an infinite distance away. So we're going to be considering orbital mechanics, that is mechanics about things in orbits. So let's start by considering a satellite in a circular orbit. Now, from the last section, we know that the gravitational potential energy of a satellite with a mass given by little m orbiting a planet with a mass capital M at a distance r from its center of mass, which is shown in this diagram here, is given by U is equal to minus g mm on r. Now we can also calculate the kinetic energy of this satellite. So we know that the kinetic energy is given by a half mv squared. Now if we consider the forces acting upon this satellite, which is undergoing circular motion, the only force acting upon it is the gravitational force. So we can say that the net force, which is the centripetal force given by mv squared on r, must be equal to the gravitational force, which is g m over r squared. So rearranging this, we can cancel out this r with one of these r's, and we can then multiply both sides by a half, and we get a half mv squared is equal to a half g mm on r. So this here is the kinetic energy. So we can see that the kinetic energy is given by g mm over 2r. Now we can calculate the total mechanical energy, which is the sum of the potential energy plus the kinetic energy, by summing together U, which was minus g mm on r, with g mm on 2r, and you can see that's going to leave minus g mm on 2r. So this tells us the total mechanical energy of a satellite in a circular orbit. Now to practice using these equations, try homework set 3, question 11 for 1121 and question 15 for 1131. Okay, so here's a question. What happens? A satellite is in orbit. It turns on the thruster, providing a force in the direction it's moving. So we've got some planet here with some satellite going around it. The satellite's moving in this direction. It turns on a thruster, which gives it a force also in this same direction. So as a result, the satellite moves to a new orbit. And we're asked what happens to the speed of the satellite. Does it increase, decrease, or remain the same? Well, in this case, when the satellite turns on its thruster, the thruster is doing work on the satellite, and the work is given by the force times the displacement, and these are in the same direction. So it's doing positive work. So this is some positive number. And we know that when we do work on something, then we change its total mechanical energy. So this is equal to the change in the mechanical energy. So we can write, well, delta E is equal to the final mechanical energy minus the initial mechanical energy. And we've just seen that mechanical energy on the previous slide, we saw that E was equal to minus GMM onto R. So we can write, well, this is minus GMM onto RF, and then minus, so plus GMM onto RI, where RF is the final radius and RI is the initial radius. And this is equal to some positive number. So if this is positive, then it means that this term here must be larger than this other term here. So we can write GMM over 2RI is greater than GMM over 2RF. Now almost everything here cancels out. That occurs on both sides. This occurs on both sides, which tells us that 1 over RI is greater than 1 over RF, which in turn tells us that RI must be less than RF. So physically, this means that the final radius is greater than the initial radius. So it moves up to an orbit something like this. So here we've got RI and here we've got RF. But this is us what happens to the speed. So to do that, we can consider the kinetic energy, because the kinetic energy is related to the speed. And we know that the kinetic energy is given by GMM divided by 2R. So if we're moving to a larger R, so as R goes up, then the kinetic energy decreases. And since the kinetic energy is also equal to a half mv squared, this tells us that if the kinetic energy is decreasing, the speed must also be decreasing. So it's possibly a surprising result, but when the satellite turns on its thruster, its speed does eventually decrease once it's stabilized into a new orbit. Okay, so here's an example problem for us. A playful astronaut releases a bowling ball with a mass of 7.20 kilograms into a circular orbit around the Earth at an altitude of 350 kilometers. So let's draw a little diagram. Here's the Earth. Here's the satellite's orbit. This is definitely not to scale. This distance here is h is equal to 350 kilometers. And some other useful data which we can get off the formula sheet is that, the data sheet is that the radius of the Earth is equal to 6.371 times 10 to the 6 meters. So this radius should be much greater than this height here. And the mass of the Earth is equal to 5.972 times 10 to the 24 kilograms. So then in the first part of this question, we're asked, what is the mechanical energy E of the ball in its orbit? So this part is not too hard, though it is a little bit tedious. So we've got that the total mechanical energy is given by minus GMM over 2R. And R here is the distance between the center of the Earth and the satellite. So R is going to be equal to H plus capital R, the radius of the Earth. So this is equal to minus GMM over 2 times the radius of the Earth plus H. So now what we can do is just substitute in numbers and evaluate. So this is minus 6.673 times 10 to the minus 11 times little m, which is the mass of the bowling ball, which is 7.2, times big M, which in this case is the mass of the Earth, because that's the other object. So we've got 5.972 times 10 to the 24 divided by 2 times now the radius of the Earth, which is 6.371 times 10 to the 6, plus the height, which is 350 times 1,000 meters. So solving this on the calculator, we get minus 2.13 times 10 to the 8 joules. So in part 2 of the question, we're asked, what is the mechanical energy E0 of the ball on the launch pad at the Kennedy Space Center before launch? So in this case, we can't use this equation here because this is the orbital mechanical energy, which describes an object in orbit, and while it's sitting on the launch pad, this object is not in orbit. It's in contact with the Earth, so there's normal forces and other things involved. So we know that E naught is equal to U naught plus K naught. Now, it will have a small amount of kinetic energy because of the Earth's rotation, but this is so small that we can neglect it, because when you think about it, omega for the Earth is equal to 2 pi radians per day, and so the kinetic energy is going to be tiny. So we can ignore this because it's approximately equal to 0. So we just need to calculate the potential energy on the launch pad. So that is given by minus g m on r, and the r in this case is the Earth's radius, and this is the mass of the Earth. So now we can substitute into here. So this is minus 6.673 times 10 to the minus 11 times the 7.2 times the mass of the Earth, which is 5.972 times 10 to the 24, divided by the radius of the Earth, which is 6.371 times 10 to the 6 meters. So solving that, we end up with minus 4.50 times 10 to the 8 joules. So we've answered the first part, and it says from there to orbit, what is the change, delta E, in the Bohr's mechanical energy? So delta E is equal to the final E minus the initial E. And we've calculated the final E in part 1. So this is equal to minus 2.13 times 10 to the 8. And then we calculated the initial E in part 2. So that's minus 4.50 times 10 to the 8. So solving this, we end up with delta E is equal to 2.37 times 10 to the 8 joules. And that's how we solve that problem. So this brings us to Kepler's laws. So Kepler's first law tells us that all planets move in elliptical orbits like this one, with the sun at one focus. So an ellipse has two focuses, and the sun which it's orbiting around needs to be at one of these. So Kepler's second law tells us that a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is, the rate dA dt at which it sweeps out an area is constant. Okay, so let's see what this actually means by having a look at a simulation, and then we'll go ahead and actually prove it. So this is a nice simulation showing Kepler's second law. So we'll start sweeping, and it's showing the areas which are traced out in equal times. So you can see here we have a wide but shorter triangle, and over here there's a much longer but less wide triangle. So you can see how the satellite is moving slower when it's further from the sun, and then when it gets round to being closer to the sun, it goes very quickly. So let's prove this. Let's consider this triangle which the satellite sweeps out as it moves through the angle d theta. Well, we know the formula for the area of a triangle is just half the base times the height. So the area of this small triangle is given by a half. Now this length here is the radius, and then the length of our triangle is the arc length, which is r d theta. So we've got a half r squared d theta. Now, what Kepler's second law is telling us about is the rate of change of this area. So to get that, we're going to have to divide by dt. So we've got dA dt is equal to, now the radius is changing very, very slowly. So we can choose d theta to be small enough that the radius is constant. So then we've got a half r squared d theta dt, and we know what d theta dt is. It's omega, the angular velocity. So this is a half r squared omega. Now, r squared omega should vaguely remind you of moments of inertia. We've got that the total angular momentum is given by I omega, and the angular momentum is conserved. So if we assume angular momentum is conserved, then I omega is equal to a constant. And we've just got a planet, a point mass moving here. So I is given by mr squared omega. So we can say, well, rearranging this, we've got this is equal to L, our angular momentum. We can replace r squared omega with L on m. So dA dt is equal to a half L on m. Now the mass of the planet is definitely not changing, and as long as we assume that the angular momentum is conserved and isn't changing either, then we can see that dA dt is equal to a constant. So we've now proved Kepler's second law. So this brings us to Kepler's third law, which tells us that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. So we've got this equation here. This one's not too hard to show, because when we consider the satellite orbiting around the planet, we know that it's undergoing circular motion. So the resultant force acting on the planet is just the centripetal force, which is given by mv squared on r. We also know what force is causing this resultant force. The only force between the satellite and the planet is the gravitational force. So this is equal to gmm over r squared. So we can cancel out one of these r's and the little m, which is the mass of the satellite. So we've still got the mass of the planet there. And so now we've got v squared is equal to gm on r. Now we know for the planet that the velocity is given by the distance divided by the time, which is 2 pi r over the period, which is t, and this is a velocity squared. So this is the velocity in here, and we're squaring it. So looking at this part of the formula, we can write, well, gm on r is equal to 4 pi squared r squared on t squared, which we can rearrange to say, well, t squared is equal to 4 pi squared, and then we've got an r squared here times an r here, so that's r cubed, divided by gm. And that is the formula which is written just here. So the square of the period is proportional to the cube of the radius of the orbit. So to practice using this, homework set 3 for 1121, try question 12, or 16 if you're in higher physics. Okay, so a question. Satellite 1 is in a certain circular orbit around a planet, while satellite 2 is in a larger circular orbit. So we can say from that that the radius of orbit 2 is greater than the radius of orbit 1. And we're asked which satellite has, in part A, the longer period. So to answer this, we're going to need to use Kepler's third law, which tells us that the period squared is proportional to the radius cubed. So if we have a bigger radius, we have a bigger period. So this tells us that satellite 2 has the largest or longest period. Now in part B, it's asking us about the speed. So possibly you remember the speed question that we did before, and we approached this one in a similar way. So to think about the speed, we know that K, the kinetic energy, is equal to a half mv squared, and it's also equal to gmm over r. So this tells us that v squared is proportional to 1 over r, or that if we have a smaller radius, we have a higher speed. So this tells us that satellite 1 will have the higher speed. So in this problem, a spaceship of mass 4.5 times 10 to the 3 kilograms is in a circular Earth orbit of radius 8 times 10 to the 6 meters with a period of 118.6 minutes or 7.119 times 10 to the 3 seconds when a thruster is fired in the forward direction to decrease the speed to 96% of the original speed. And part A asks what is the mechanical energy of the satellite in its new orbit, and part B says what is the period t of the resulting elliptical orbit. So in this problem, we've got a spaceship with a mass of 4.50 times 10 to the 3 kilograms. It has got initially a circular orbit with a radius of 8 times 10 to the 6 meters per second, and its initial period is equal to 118.6 minutes, which is equal to 7.1919 times 10 to the 3 seconds. So it's thrusters fire, and that decreases the speed to 96% of the original. So if we've got the final speed is equal to 0.960 times the initial speed. And in part A, we're asked to find the mechanical energy of the orbit. So the easy way to do that would be to just substitute into the formula minus gmm over 2a. But in this case, we don't know what a is, so we can't just solve it this way. So instead, we're going to have to look at E is equal to U plus K and calculate U and K separately. Okay, so the potential energy, U, now just after the thrusters fire, it's still going to be at radius r. So when a rocket fires its thrusters, it doesn't suddenly disappear from the spot it's at and reappear somewhere else. It stays at that radius for a short amount of time, but firing its thrusters will make the radius of the orbit eventually change. So we can say this is equal to minus g mm on r, and this r is the initial r that it was at. So this is equal to 6.673 times 10 to the minus 11. Now times the mass of the Earth, which is 5.972 times 10 to the 24, times the mass of the satellite, which is 4.50 times 10 to the 3, divided by r, which is 8.00 times 10 to the 6. Sorry, that shouldn't be meters per second. I've miswritten the units for there. That should be meters. And so solving this, we get U is equal to minus 2.42 times 10 to the 11 joules. Now the other thing we're going to have to find is K. So it does slow down straight away. So we're going to need to find the final kinetic energy, which is a half mv final squared. Okay, so to do this, we're going to need to calculate V final, and we know that it's 0.960 times V initial. Now, we can work out V initial because we have the period and the radius of the original orbit. So we can say, well, V initial is going to be the distance it travels, which is 1 radius, over the period, which is T0. So this is 2 pi times 8 times 10 to the 6 divided by 7.119 times 10 to the 3. And solving this, we get the initial speed as 7,061 meters per second. So the final speed is equal to 0.960 times 7061, and that is equal to 6,778 meters per second. Okay, so now we can substitute in here. So we've got a half times 4.50 times 10 to the 3 times the 6,778 squared. And solving this on the calculator, we end up with 1.034 times 10 to the 11 joules. Okay, so now we've got the potential energy and we've got the kinetic energy just after the thrusters have fired. So now we can calculate the total mechanic energy just by adding those together. So we've got minus 2.42, sorry, I left off a 2 here, 2.242 times 10 to the 11 plus 1.034 times 10 to the 11, and that gives us minus 1.208 times 10 to the 11. And then since most of the things were given to 3 significant figures, we should give our answer to 3 significant figures. So this is minus 1.21 times 10 to the 11 joules is the total mechanical energy just after the thrusters have fired. So for part B, we're asked to find the period. To find the period, we're going to have to go back and use Kepler's third law, the law of periods, which tells us that T squared is equal to 4 pi squared over gm times a cubed, or r cubed for a circular orbit, a cubed for an elliptical one. So in order to do this, we're going to need to find a, but as we highlighted up here, we can use E, our total mechanical energy, now to find A, as A is now the only unknown in this equation. So our next step is to find A. So let's rearrange this equation in the purple box, and we can say, well, A is equal to minus G mm over 2E, which is equal to minus 6.673 times 10 to the minus 11 times 5.972 times 10 to the 24 times the 4.50 times 10 to the 3, all divided by 2 times, and this is minus 1.208 times 10 to the 11. So we enter all this into the calculator, and when we get that, we get A is equal to 7.423 times 10 to the 6 meters. Okay, so now we've got A, so now we can find T. T is equal to 4 pi squared over G, which is 6.673 times 10 to the minus 11, times M, the mass of the planet, which is 5.972 times 10 to the 24, times A cubed, which is 7.423 times 10 to the 6 cubed, and then we need to take the square root of this. So when we do all that on the calculator, we end up with 6,365 seconds, which is equal to 106 minutes. So that's how we solve that problem. So in this problem, a 20 kilogram satellite has a circular orbit with a period of 2.4 hours and a radius of 8 times 10 to the 6 meters around a planet of unknown mass. If the magnitude of the gravitational acceleration on the surface of the planet is 8 meters per second, what is the radius of the planet? So we need to try and find radius. So let's start by considering an object on the surface of the planet. So consider an object on surface. Then we know that the gravitational force is mg, where little m is the mass of the object, and we know that that's equal to gm on r squared, where capital M is the mass of the planet and capital R is the radius of the planet, and this is because the object is a distance r from the center of the planet. And so the mass of the object cancels out, and we can write this as r squared is equal to gm on little g. Now the problem here is that the mass of the planet is unknown. So we're going to have to come up with another expression to find the mass of the planet so that we can get this radius here. So to do that, let's consider the satellite in orbit. And for the satellite in orbit, we know that it obeys Kepler's laws, and in particular Kepler's third law, which tells us that the period squared is equal to 4 pi squared on gm times r cubed. And so we can rearrange this to get an expression for m. So we can see m is equal to 4 pi squared r cubed divided by t squared g. And we can now substitute this back up into this equation. So we've now got g on g times 4 pi squared r cubed divided by the period squared times g. So our universal gravitational constant cancels out from the top and the bottom, and now we can substitute in the values from the question. So we've got 4 pi squared times r cubed, which is 8.0 times 10 to the 6, so that's cubed, divided by little g, which was 8, times the period squared, and the period is 2.4 hours. So it's 2.4 hours, and then there's 60 minutes in an hour and 60 seconds in a minute. So that is squared. So we can then solve this on the calculator, and we end up with 5.8 times 10 to the 6 meters. And I've given this to two significant figures, as the values in the question are all given to two significant figures. So in this problem, we're told that one way to attack a satellite in Earth orbit is to launch a swarm of pellets in the same orbit as the satellite, but in opposite direction. Suppose a satellite in a circular orbit 500 kilometers above the Earth's surface collides with a pellet having a mass of 4 grams. Part A, what is the kinetic energy of the pellet in the reference frame of the satellite just before the collision? And part B, what is the ratio of the kinetic energy to the kinetic energy of a 4-gram bullet from a modern army rifle with a muzzle speed of 950 meters per second? Here's the Earth. We have a satellite here which is at a height of 500 kilometers above the Earth. Got radius of the Earth here. So again, not to scale. If we want to get the radius of the orbit, then it'll be the radius of the Earth plus the height. So that'll be 6,371 plus 500 kilometers. So in this question, we're told that one way to attack this satellite here is to launch a swarm of pellets which are traveling in the opposite direction. Now, to be in the same orbit, when they're moving in the opposite direction, they're going to have the same speed, because the speed is set by the height of the orbit. And we're told we can assume that the mass of the pellets is equal to 4 grams. And then in part A, we're asked what is K of bullet in frame of satellite. Okay, so to work out K, we'll need to go back to our equation that we learned ages ago. The kinetic energy is equal to a half mv squared, but this tells us that we're going to need to know, well, what's this v here of bullet in satellite's frame. So we're going to need to use what we're told in the question to work out the speed of the satellite, and then once we know the speed of the satellite, we know that the speed of the bullet is equal and opposite to that, so then we can get this relative velocity here. Okay, so we know that the kinetic energy for the satellite is equal to g times the mass of the satellite times the mass of the Earth over 2r, let's put little s there, and that this is equal to a half mass of the satellite times the speed of the satellite squared. So we can use this equation here to get the speed of the satellite. Now looking at this, we can see there's a couple of things which will cancel out. The mass of the satellite will cancel out, and these halves, the 2's on the bottom, will also cancel each other out. So we can rearrange this to get an expression for the speed of the satellite. So the speed of the satellite is equal to g times the mass of the Earth over r. And so this tells us that v is equal to square root of g times the mass of the Earth on r, where r was defined over here. Okay, now the speed in the satellite's reference frame, it is at rest and it has the bullet traveling towards it. The velocity of the bullet relative to the satellite is equal to the velocity of the bullet minus the velocity of the satellite. And in this case, the satellite is going this way with some velocity, and the bullet is going this way with some velocity, same velocity, but in opposite directions. So this expression, which we've just derived, defines both of these. This negative sign here will mean that these two end up adding together. And so we have that the velocity of the bullet relative to the satellite is equal to 2 times g times the mass of the Earth on r. Okay, so now we've got the relative speed, so that's what we needed to put in here. So k for the bullet in the satellite's reference frame is given by a half times the mass of the bullet times 2 root gme on r squared. And so this is equal to 2 mg times the mass of the Earth over r. And then we can substitute in, so we've got 2 times 4 grams, so that's 4 times 10 to the minus 3 times 6.673 times 10 to the minus 11 times the mass of the Earth, which we grab off the data sheet, 5.972 times 10 to the 24 over r, which is here. This is 6,371 plus 500, and then that's kilometers. So we times it by 1,000 to get it into meters. Solving this, we end up with 463,992, which we can write as 4.6 times 10 to the 5 joules, two significant figures. Now, part B asks us to compare this kinetic energy of the orbital pellets to the kinetic energy of something coming out of a rifle with a muzzle velocity of 950 meters per second. So to get this kinetic energy, we just do a half mv squared, which is equal to a half times 4 times 10 to the minus 3 times 950 squared, which is equal to 1,805. So to get the ratio of K in space over K from rifle, we do 463,992 divided by 1,805, and that gives us 257 or 260, two significant figures. So the moral of the story is here, you don't want to get hit by orbital debris traveling in the opposite direction to you in your orbit in space. It has a lot more energy than equivalent amount of matter coming out of a gun on Earth. So it would do a lot of damage.